Today I have prepared everything in advance. So we are already here. I haven't read the problem yet. And on this last day of 2025, I hope you had a good year. I hope the next one will be even better. Now let's jump into that. So a tree is an undirected graph that is connected and has no cycles. Okay. You're given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. The graph is represented as an array of edges of length where okay, so it's basically all the edges. Indicates that there is an edge between nodes AI and BI in the graph. Okay, interesting. So return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. Sounds good. We have just one edge added. This will be important. But first, so there can be basically cannot be two cycles. So we need to return the answer that occurs last in the input. We will be adding edges to the tree, and we will be slowly building this tree. And once we encounter the first cycle, basically the edge that connected, yeah, the cycle, it will be tricky to discover. But let's take it step by step, right? So we are giving a graph. We are giving edges. Edges is a list of integers. So always this internal list is of length 2. And we need to return an edge. So we will be returning a list of integers also of length 2. And then let's see tests. Okay, so let's say it was 1, 2, 3, and then it was 4 and 5 and 6 and this edge, right? Maybe let's make it a little bit shorter just for our convenience. Okay. So what is the edge that we should return here? It will be one of those 4 edges that are connecting this cycle here. Whichever is the last one of those, this one will be the one that we need to return. Now, what's the problem here? The problem is, how do we discover quickly and easily that adding an edge creates a cycle? The thing is that we can be given a list of edges that are like random. So for example, we can be, for this particular graph, we can be given 2, 3, and then 4, 5, and then 3, 1. So now we are basically having 2 unconnected graphs, right? One is this one, another one is this one. And then we are connecting this graph. So it will be, let's say 3, 4. We'll be connecting this graph. And then finally we are adding an edge 5, 1. And here we will detect the cycle. So one of the ideas that I had about the solution. So in here we will be, just to be clear, we will be returning 5, 1. But one of the solutions that I was thinking about was that let's just order the edges. I was thinking that if we order the edges, right? So we will have to slowly propagate through the edges. So for example, if there is an edge, we can also order the numbers inside the edges, right? So we will start with 1, and it will be 1, 3, and 1, 5. And then it will be 2, and it will be 2, 3. And we are connecting this. And then it will be 3, 3 to 4, and we're connecting this. And then it will finally be 4 to 5. And this will be the last edge. So once we find an edge that has both numbers already mentioned before, this is the edge that we should be returning. So is this the case? Is this always the case here? So yes, if it's a tree that is unconnected, no. We also have this issue, right? Like, for example, let's say we first connected these two, and then we connected these three, and then we connect this, so 4 and 3. And that's what I'm trying to prevent, right? This situation where we first connect these two and then we connect this one. That's what I want to prevent by ordering all our edges, because then we will always just like keep growing the same tree until we get to the cycle. So this seems to be a solution. Basically, first order all edges. Then iterate over edges and remember visited nodes. Once both ends are visited, this is the edge. The problem here is that we will just detect the cycle. Oh, I forgot to set up the time. Okay. We will just detect the cycle. So it will be some ordered edge inside the cycle. But I don't want to do this. I don't want the problem is that I need to return the last edge that came as an input. So if we reorder the edges, it can be the same cycle. So I already know that it's part of the cycle. I can try to find the cycle and then figure out which of the edges in this cycle was the last one in the input. But that's obviously a very inelegant solution, but not the last one input, but not necessarily the last one in the input. Okay, so this, and also it will be like require ordering of edges, so it will be O of m log m, at least where n and m is, as usual, number of nodes and number of edges. So let's think about something else. Should we do some topological sorting here? Sort. So we can reproduce this graph. Yeah, so currently we have these edges. We can create a graph where we start to do DFS. But yeah, again, the problem will be that how do we find which one occurs last in the input? So we can build a graph and it will again kind of reorder all the edges. So yeah, I think the idea is either way to find a cycle and then to find all the edges in the cycle, and then to find which of those edges is the last one in the input. It still sounds like something tricky. Is there a simpler solution? So let me try another example. Okay, here, let's say I change the ordering to this. So now it will be 3, 4 that I need to return, and let's actually have this 2, 3 as the last edge. So I don't even know. Okay, so 4 to 5. How do we even find the cycle in this graph, right? How do we detect the cycle? Detecting the cycle is easy with like, you can mark something as visited, like do BFS or DFS, and if you visit it again, you detect the cycle. How to find all the edges that can be attributed to cycle? That's a trickier problem. From the top of my mind, I don't know how to do that. Yeah, I think one of the solutions here, yeah, it actually makes sense. So yeah, interesting. So what we can do is we can count, is kind of a topological sort. So let's count the number of times that each node is mentioned. So we will count this, and we can see that nodes can be mentioned different numbers of times. So what do we do then is like all nodes that are, there will be nodes theoretically that are mentioned just once, like 2, for example, right? So we are removing the edges associated with those nodes. So we will be removing this like 2 to 3 edge, and we will be subtracting corresponding numbers for the corresponding counts for all of these edges. So yeah, it will also require us to like quickly add and remove numbers from different counts. So it will require us to keep counter. But yeah, we will do it time after time. Eventually, there will be no nodes left that have just one connection, like here, for example, right? If we remove this node. So if that situation happens, then we know that all of the current edges are part of the cycle. So then we just need to find which of these edges that are part of the cycle was the last one in the input. And yeah, that sounds like a plan. Okay. I'm trying to think about like an elegant solution for how to find the mapping between the edge and its number in the input. But yeah, I think the easiest solution will be just to iterate over the input and find if the edges in the graph or not. Okay, so yeah, it's kind of a topological sort with removing of edges. So let's think what it will cost us in terms of runtime. So identifying all the edges that all the nodes that have just one edge, incoming or end or outgoing edge, will be of m, and then each operation, like basically in total it will be O of m operations, because we will be quickly doing this. Yeah, I think it will be O of m in total. We need to write the algorithm to figure it out, certainly. But essentially there is like at most of n nodes that have just like one edge connecting to them. Removing those will be of n, and then we don't need to consider those edges again. And yes, in total we can remove this way m of edges, and each time we are removing one edge. So the total number of operations will be on the order of m. So that's the first step for removal of edges. Then once we remove all the edges, we will still have edges in the cycle, and we will need to iterate over the input edges. So of m is an input, and yes, we will need to iterate, and we will keep track of whether this edge is in this cycle or not. We can probably create a set for that, so it will be of n for iterating iterate over input and check. And so in total it will be of m for this particular operation. And yes, it will be of m to construct the counters, because we will be iterating over all edges, and for each we will be doing exactly 2 operations to add for the nodes. So of m in total. Okay, implementation. So first of all, we need to create counters, and we also need to create counters pointer from specific counter to the nodes that have this amount of edges ingoing or outgoing. So count to nodes will be equal to default tick offset, I think, for rapid removal and rapid add of one of things. So then count to nodes, this is good. Do we need to do anything else? Yes, node to count will be equal default dict of integer. Okay, I think that's fine. So now first we are constructing those data structures, and it means for start and in edges. Let's actually make it just a dictionary, because it will be a bit cleaner here. So node to count will be equal current count equal node to count start. Let's maybe do it as a function. Yeah, let's create a function. Def increment count for node, because we will need to do it both for start and end, and it's cleaner this way. So first of all, current count is equal node to count get node for 0, new count is equal to 1. So if current count bigger than 0, then it means that we need to remove count to nodes of current count, remove node, and then we need to do node to count node is equal to new count, and count to nodes of new count add node. So the node is an integer, and we are not returning anything. We are just incrementing this dictionaries. Okay, so I think we will also need to decrement count for node when we will be popping those, right? So node is an integer. We are returning none, and we are doing pretty much the same thing as we were doing. So here it's better, like if we are mistaken, it's better to fail explicitly, because the invariant here that if we are decrementing count, the node always has a count bigger than 0. So new count is, what did I do here? Strange thing. New count is current count -1. Okay. So if current count, if new count is equal to 0, do we need to do anything? Yes, we can clean this up, but we might as well just leave it be. So node to count, no, we need to do current count remove node, node to count node equals to new count, in counts nodes new count equal add node. So yes, and we had default diff to 6, so we will have some nodes here with 0. This is fine. I actually didn't mention space complexity. So space complexity n definitely, so because we keep counts for all the nodes. Do we also add anything for the edges? I don't think so. So far it's unclear whether it's O of n plus m space or just O of n space. I think it's O of n. Fine. Now we have functions to increment and decrement the count. So for start and node and edges, we need to increment count start and increment count end. Okay, cool. So now while length of count nodes of 1 is bigger than 0. So while we have nodes that have just one incoming / outgoing edge, we need to iterate over these nodes and remove the corresponding edges. Oh, yeah. The problem is, how do we know the corresponding edge at this point of time? We are not removing the specific, we are just removing the node. So what do we need to change to keep track of edges themselves? So these edges that we are removing will always have just one possible corresponding node. So we just need a graph structure that also keeps all the nodes and all the edges. I think it will, in the end, will be of m+m space. And we will need graph, which will be default dictionary of, is it set? Yes, I think it should also be set. Set. Okay, define now let's just do for start and an edges. Graph start and end, graph and start. So now these two are pointing to each other. Now for node in count nodes 1. All of those nodes have just one such edge. Yes, I get it. 20 minutes have passed. Actually, already almost 30 minutes have passed. So let's continue. We now need to be very careful about what exactly do we do when we are removing the node. So first of all, we need to remove the edges. So this will be start equals node and equals graph start, and we need to create a list and we need to do pop. It will just always be a set of size 1. So we will be now removing this here. So we have already removed this part. Now for graph end, we need to remove start. So this is where we remove end in the graph for the start. Okay, actually we are not. Let's do that maybe. Graph delete graph start, because this is now fully removed. That's fine. And now we do decrement count for start and also decrement count for end. Okay, so now we only have edges that are part of the cycle. And the only question that we have left is how to accurately traverse through these and like how to figure out which one is the last edge. So yeah, for each non-removed start, okay, so all edges is all cycle edges will be equal to set, and we will add both directions here. So for start in graph, for node in graph start, for add start end, and now for edge for start and in edges, last edge equals none. If start and end in edges, if start end in all cycle edges, so it means that last edge equals start end. If end start in all cycle edges, last edge equals end start. Return last edge. Okay, this was crazier than expected, and I haven't gotten in the depths of how exactly these data structures work. So I don't think this is a very good solution. And yeah, we now have OFM plus n runtime in total because of how we need to create. Okay, actually, for this particular graph, we have corresponding number of edges and nodes. So yeah, basically, they're the same O. So it can O of M and O of N in this scenario are the same thing. So we can just change all of this to O of M or O of N because it's a tree with one additional edge. So it cannot be like more connected where M starts to dominate. So basically N dominates here and it's similar to the number of edges, total number of edges. And it cannot be that the graph is unconnected, so there cannot be too many nodes compared to the number of edges. So here we have of n essentially of n runtime and space because of n is similar to of m. Okay, so I think I will just try to pass this problem. Yeah, set size change during iteration. Oh, for node and counter nodes. List counter nodes. Okay, so that's strange. We are almost correct. The only thing we are returning the correct answer. We are just returning it. So now this will pass. Yep, I solved this problem. This is really strange, but yeah, I have passed this problem. Now I will go and check what is the actual nicer solution, because obviously there is something more like faster, but I have still figured out the best possible solution in terms of time complexity and space complexity. It cannot be faster than that, but there can be a faster algorithm. So see you all next year.